Hi, welcome. This is the CPU optimization module. The goal of this module is to help admins get a better handle on optimizing for CPU use. In fact, all of these optimization modules are there to help the admins get a better handle on using the appropriate tools to monitor the different resources. In this case, of course, it'll be CPU. All of these optimization modules all introduce the resource a little bit more of a deep dive into that resource. And that's important because understanding what to look for is a critical piece in understanding this. We'll also introduce the tools, the primary tool, ESXtop, to help monitor each of the different resources. So our goal here is to understand that multiple VMs can run on the same host, right? Be able to run lots of virtual CPUs and be able to consolidate workloads, but do it to a degree where the consolidation ratio does not cause a CPU bottleneck. So we need to understand a bit more on the CPU virtualization concepts. That's our first lesson. Second lesson, we'll take a look at how the NUMA architecture is configured in vSphere. In the third lesson, we'll introduce ESXtop if you haven't seen this tool before, so that we can then properly use it in monitoring CPU use in lesson 4. So let's start off with our first lesson, CPU virtualization concepts. In this lesson, we'll discuss the CPU scheduler features and discuss what affects CPU performance. So again, we want to be able to promote a highly consolidated environment with a good number of VMs and their virtual CPUs. So the goal of the scheduler is going to have many functions here. In our list, we select from of the many features. The job here is to schedule virtual CPUs onto logical cores. We'll take a look at what that means a little bit later. The scheduler will enforce what's called the proportional share algorithm for CPU use. The scheduler supports symmetric multiprocessing VMs. We call that VSMP for virtual symmetric multiprocessing. And the system uses a relaxed co-scheduler for those multi-CPU VMs. The scheduler is also aware of the different types of topologies out there, whether you have a uniform memory architecture or non-uniform memory architecture, as well as cache topology too, and will adjust how it schedules the virtual CPUs accordingly. So first things first, how does the scheduler actually see a virtual machine? The scheduler sees a virtual machine much like how a traditional OS sees a multi-threaded process. In a traditional OS, a multi-threaded process will be represented by a process identifier, but the actual schedulable components are known as lightweight process, and they'll be represented by lightweight process IDs. In the case of VMs on the ESXi server, the VMs are made up of individual schedulable components. Those are known as worlds. And the VM is basically a group of worlds. So the VM is actually represented by a group identifier, and the worlds are actually represented by world identifiers. So in any case, in doing CPU monitoring, we need to monitor individual worlds sometimes. And so what are the different worlds that make up a VM? The most commonly monitored world in any VM would be the virtual CPU worlds. VMs are made up of, quite a few different worlds, but the most important ones for CPU monitoring are those virtual CPU worlds. So keep in mind, for however many virtual CPUs a VM has, that's also the same number of CPU worlds that will exist in the VM. So if the VM has one virtual CPU, it'll have one virtual CPU world. If a VM has 4 virtual CPUs, it'll have 4 virtual CPU worlds. Now there's all these other worlds that make up a VM. We just show an example here where there's a world that represents the VM's console. That's called the mouse, keyboard, and screen world, or otherwise known as MKS or VMX-MKS. There's also a world that represents the SVGA device. That's the VMX SVGA. I know this is just a couple examples. There's, again, depending on how much virtual devices you assign the VM and what version of vSphere, will ultimately end up determining how many worlds that a VM is actually made up of. And the goal of the scheduler is to choose which world to schedule onto any logical core out there. So other features. The scheduler is there to allocate the CPU resources and coordinate CPUs for the different virtual machines. The scheduler actually will wake up on a sliding scale interval, pretty much to use a dynamic and transparent resource allocation scheme. It'll wake up anywhere between 2 to 30 milliseconds and migrate the virtual CPUs as necessary. The scheduler will also schedule the virtual CPUs to run on logical cores. They basically have a built-in time slice of 50 milliseconds. So that's the VM kernel's default for when there isn't any contention on the system. If there is contention though, well then the virtual CPUs will have to wait in a queue, right, for the other virtual CPUs to be available for the logical CPUs to be available for virtual CPUs to be scheduled onto them. Ultimately, how much time that any virtual CPU will be granted onto any logical CPU will be determined by the combination of their CPU reservation, their CPU limit, and their CPU reservation and their CPU share. All three of those calculate how much time a VM is going to, be able to obtain while on that virtual CPU. It also helps determine their priority as they are sitting in that queue. So just keep in mind it's this time slice, algorithms, but also the prioritization will be determined based on the resource allocation settings. Also, the scheduler supports a multi-CPU VM capability, right? We need to be able to support vSMP, right? In fact, these versions of vSphere, a VM can conceivably have 256 virtual CPUs. Now, you would never do that unless you actually had the real CPUs to support that. You need at least 256 logical CPUs in order to schedule a 256 virtual CPU VM. So what's a logical CPU? Well, that all depends on whether or not you have hyperthreading or not. If you have hyperthreading, then a logical CPU is essentially a hyperthread, which is going to essentially be one of two schedulable entities on an actual core, right? Typically, if you've got no hyperthreading, then each core is the schedulable entity for that processor. And so if a server has, say, 24 cores on a socket, you've got the ability to have 24 things scheduled at any one time. But with hyperthreading, that doubles it to 48 because you end up having two separate schedulable entities on the cores with hyperthreading. So when it comes to scheduling a 256 virtual CPU VM, you conceivably need to have 256 schedulable slots on the system, which means it's 256 logical CPUs technically to make that VM work. But that wouldn't be optimal because then the VM's virtual CPUs will need to be sharing two of the virtual CPUs on each and every core, which will most likely cause some inefficiencies in how the VM can run its virtual CPUs concurrently. So ultimately, for any VM that you schedule, make sure the actual number of virtual CPUs is able to fit with the proper amount of physical cores. So while the system does use logical CPUs to schedule things, you really need to count cores for pretty much anything when you're looking at CPU requirements. So if a VM has, say for instance, 4 virtual CPUs, you need 4 cores, right? Even though you could conceivably run on 4 hyperthreads, ultimately you want to have 4 cores as a general best practice. But what I'm also saying is you don't want to have a VM that is larger than it needs to be, right? We can create a VM with that great number of virtual CPUs, but we need to be able to handle that as efficiently as possible. One way the system does that is it uses something known as a relaxed co-scheduler. What that basically means is a VM who has multiple virtual CPUs, not all the virtual CPUs need to be scheduled simultaneously on the actual physical hardware. If the VM actually only needs a small subset of its total number of virtual CPUs, those virtual CPUs can be scheduled and their scheduling interval can be run at a higher rate than maybe other virtual CPUs in the VM that aren't being used. So this actually allows the system to schedule the virtual CPUs on a much more granular level. The scheduler will actually consider skew when scheduling these virtual CPUs in these multi-CPU VMs so that the virtual CPUs can progress at faster rates than other virtual CPUs within the same VM. And virtual CPU skew will increase when it's not making progress, but one of its sibling virtual CPUs is. This is when you have possibly a mixture of workloads in the same VM where sometimes they need all of the virtual CPUs and sometimes they don't. And so the virtual CPU is considered to be in a skewed state if the execution rates between the virtual CPUs in the VM exceed a threshold, usually more than a few milliseconds. So this form of relaxed co-scheduling allows the scheduler to have the VM having its virtual CPUs all being executed at slightly different execution rates. This decreases the number of physical resources and CPUs to be able to do a co-start, and it will increase your overall CPU use. What this doesn't do, though, is it doesn't mean you should go out and build these really, really big VMs when you don't really need to. What it does allow for is having VMs that sometimes need all of their virtual CPUs and sometimes they don't. The system creates a much more efficient way to schedule this. But watching out for co-stops is actually something to look out for because that might be an indicator that your VM is consistently not using all the virtual CPUs that it gave it. So let's take a quick look at some of the CPU features. We'll come back and take a look at what are the things that impact CPU performance after this quick break. So see you in a few minutes.